In this lesson, we're going to look at some calculations using the gas law equations. So the first thing we want to do when we're looking at a gas law problem is we want to see which variables are involved so we know which equation to use. So we start by reading the problem. I see a balloon has a volume of 2.6 liters. So now I have a volume, and I label it V1 because it's the first volume I get to. It really doesn't matter as long as my volume and temperatures or whatever variables get paired together correctly. So 2.6 liters inside the store where the temperature is 22 degrees Celsius. So that's going to have to be T1 because that corresponds to that particular volume. It says, what is the volume of the balloon when taken outside the store where the temperature is 36 degrees Celsius? So it's asking for V2, and it's giving us a T2 of 36 degrees Celsius. So I see that my variables that are changing are volume and temperature. There's no mention of a pressure change, there's no mention of change in amount of gas, so I can assume that those are constant. And so this actually becomes a Charles law problem where I have V1 over T1 equals V2 over T2. And I picked that one because the variables that change and the variables given in the problem match the variables in the equation. So when I look at this, I notice that my temperatures are in Celsius, and so no matter what, my temperatures must be in units of Kelvin. So I'm going to add 273 to each value. So 22 plus 273 will be 295 Kelvin. So I just added 273. I'm going to do the same thing for the 36. I'm going to add 273 and I get 309 Kelvin. So those are the temperatures I have to use in the equation. Okay? Now, had it been given in Fahrenheit, I would have first had to calculate to Celsius and then go to Kelvin. But most of the time in science, what you'll find is that temperatures are given in Celsius or Kelvin. So we have V1, which is 2.6 liters, over my T1, which is 295 Kelvin, and I group those together because it's describing the same scenario. Those are the paired conditions. And I'm trying to solve for V2, and my temperature is 309 Kelvin. Okay. So now it's a matter of using my algebra. I'm going to multiply both sides by 309, and so what I end up with is 309 times 2.6, okay, divided by 295, and I get 2.7 liters equals V2. So I multiply both sides by 309, and then I combine those numbers mathematically and get my volume of 2.7 liters. And then I want to ask, is this reasonable? So I know that volume and temperature are directly proportional, so as the volume increases, the temperature must also increase. And so my temperature increased, my volume increased, and so this is what I would expect to happen. So here's another problem. Cyclopropane is a general anesthetic. A 5-liter sample, so it gives me V1 equals 5.0 liters, has a pressure of 5 atmospheres, so P1 equals 5.0 atmospheres. What is the volume of anesthetic? So V2 equals question mark, given to a patient at a pressure of 1 atmosphere. That'll be P2. Now notice it doesn't matter which set I label as V1 P1 and V2 P2 as long as the V1 P1 are describing the same conditions and the V2 P2 are describing the same conditions. Now in this one it tells me that we're at constant temperature. It also doesn't mention adding additional moles of gas, so that I know that temperature and moles are constant. So T and N constant. And the gas law that relates those is Boyle's law, so I know P1 V1 equals P2 V2 because those are the variables involved. So P1 is 5.0 atmospheres times volume 1, which is 5.0 liters, equals V2, which is my unknown, times my P1, 1.0 atmospheres. Now for pressure and volume, it doesn't matter what units the values are in as long as V1 and V2 are in the same units and P1 and P2 are in the same units. So we don't have to worry about it like we do for temperature. And so what we end up with when we do 5 times 5 is 25, divided by 1 is 25. So V2 equals 25, and it's going to have two sig figs, and it's going to have units of liters, because again we have ATM and ATM. This is in liters, so our volume must also be in liters.